Hey, okay, students. Look like some of you are getting near the end of the material and getting ready for the exam. That's great. And I got a question or two on this one. This is a hard one. It's from the university book. Actually, it's not as hard as it looks at first, but it illustrates an important technique, and that's why I thought I'd pick it. Now, I got to admit, it's probably more of an important technique for the engineers than it is for the life scientist. But we do this a lot in engineering here, and let me illustrate, because we often have a long chain or a long series of the same things. Like here it says, consider an infinite long chain of resistors shown below. What is the resistance between each terminal? Maybe an example like this is the distribution of power or of data. Let's say you're working for Spectrum. What would happen is you would hook a coaxial cable up here and you would have your first customer. And so a little bit of current would go to customer 1. Then it would continue down the coaxial cable, so there'd be a little more resistance, and then it would go to customer number 2. It would continue on down the cable and go to customer 3, customer 4, 5, 6, and you might have thousands or thousands of customers along this line. Now, it's probably not an infinite number, but it is still a big, big number. Because here's the little trick, if you will, that we're going to play here. And so imagine, if you will, so I've got point A here, and let me just kind of separate out first customer of our power distribution. This could be Edison too, by the way. This could be power along a line, but usually they're not the same loads. But anyways, some idea. And let me also then group maybe this together. Okay, so here's R, and here's R, and here's R. And then let me just draw a little break and go, here's customer 2, and then another line down to customer 3, and a return line for the data or power. Okay, so, and then on down, let's see, here's customer 1, 2, 3, and so customer 4, and then on down to customer 5. Anyways, and this continues, but here is the idea. It says, what is the equivalent resistance? And we've got a mess of stuff, and they're not really series or parallel, at least written the way they are here. But what I want you to see is if I remove then the first customer and the line connecting to the second customer. And so I just have from second customer and then the line going to the third and third customer and line going to fourth and fourth customer and so forth on down. Hopefully you can see that all of this is identical to that. I mean, granted, there's one less resistor, but you're talking about an infinite number, and if you take infinity and minus 1, you still have infinity. Or in reality, these are thousands of customers, and so you have near the same equivalent resistance. And that's the trick to anything that continues on and on and on. You did that a lot in your calculus class, or depending on your calculus class. If you had the higher level calculus for engineering, you probably analyzed infinities a little bit better. Whereas if you just had the, well, at our school we'd call calculus 130, and I forget what they call it exactly, but it has some other title. I guess I should look it up. Anyways, you might not have studied these infinities very long, but they do become a very powerful tool, and that's what this technique is. And like I said, we do that a lot. We do that in construction. We do that in electrical engineering. And so like I said, this is kind of a data transmission. And so, I could be looking for Spectrum or Cox or AT&T or something like that. Okay, because watch this now. So now what we can do is rewrite this and trying to figure out the equivalence between A and B with the idea that all the other customers on down also have an equivalence. And that's a much easier circuit, and that's kind of the magical step. And so you got to kind of see infinities and how to deal with infinities, and that's really kind of the point of this problem. And like I said, it's a very useful and universal problem solving technique. All right, so now let me do this. Let me study this circuit, where this equivalent represents these, and I'll just say there's 1,000 customers. So this represents the equivalent. This is the 999 other customers on the line. And if I look at that, then these would be in series. And so the equivalent of these three would be R plus the equivalent of the whole thing plus another R. So that's 2R plus the equivalence of the whole thing. So I could then draw the equivalence of the whole thing as two resistors in parallel. And then so finally, using our parallel equation, we could say R in parallel, I'm going to call it though equivalent. Now maybe I'll just start with the way your book does it, R parallel, is 1 over the first one plus 1 over the second one. And so now I have an equation that's going to take a little bit of algebra here, but I can solve for the equivalent resistance as a function of R. Okay, so now that we have an equation to work from, let's go ahead and do the algebra here. And so maybe I'll just leave 1 over equivalent alone, and over on the other side I will get a common denominator by multiplying the two together. And that means I would have a 2R plus R equivalent here, and then plus an R, which means this numerator is 3R plus R equivalent. Okay, so then I can cross multiply, so that times 1 is R times 2R plus R equivalent. And when I cross multiply here, I get 3R equivalent plus R equivalent squared. If I distribute this, this becomes a 2R squared plus an RR equivalent equals 3R equivalent plus R equivalent squared. Now keep in mind I'm trying to solve for R equivalent, so let me write this in the standard quadratic form, and I'll write R equivalent squared, okay? And it looks like when I bring this to the other side, I'll subtract an R, so this would be 2R equivalent. And when I bring this over to here, it's minus 2R squared. Okay. Now, I just use the quadratic equation. So to get the equivalent, remember it's the opposite of b plus or minus b squared minus 4ac all over 2a. So in this case, opposite of b, so b would be a negative 2r, so I'll just call that a 2r, plus or minus, and then b squared would be 4r squared, right here, minus 4 times an a, which is a 1, and a c is a negative. Let me put the negative here, and it would be a 2r squared all over 2a. Continuing on, I would have a 2r plus or minus, and it looks like this 4 times 1 times 2, that's 8. 8 plus 4 is 12 r squareds over 2. Maybe I could think of the square root of 12 as the square root of 4 times the square root of 3. So that what happens here is this square root of 12 then becomes a 2 root 3. And then I'll also do the square root of r squared all over 2. And it looks like factoring out a 2 and then canceling it leaves me with an r plus or minus root 3r. And then finally, recognizing that the square root of 3 is more than 1, it's about 1.7, I'll drop the negative for the equivalent resistance. Okay, and well, that would be a fun discussion about the negative, but let's just go to the must be positive answer. And then this would be r, and then be 1 times root 3, which I usually like to write as a root 3 plus 1 times r. All right, hope that helped. Oh, bummer. I just looked at the answer, and they got a minus sign between these two. And I see right where I messed up. Hopefully you noticed it, and I apologize. But right here, when I had a 3 and I brought it over, I don't know why I put -2, but I did. And that should have been, let me do a correction in green. That should have been a positive, which then right here, when I put in the negative b, should have left that as a negative. Should have left that as a negative, which then would have left that as a negative, which would have left that as a negative, which would have left that as a negative. So the correct answer would be root 3 minus 1. Okay. Sorry about that little sign error. All right. Hope that helps.